Okay, these are the notes for section 4.2, and this is probably the most important lesson in all of trigonometry. It's called the unit circle, or you'll hear me call it your trig BFF. The unit circle is going to be your best friend to help you solve all kinds of trigonometry problems. So in order to use the unit circle to its fullest potential, you really need to get to know it well. You need to be able to create it on your own from scratch, from memory. And not that you have to memorize it, but you have to memorize how to create it. So we're going to go over some of the pieces of creating it. We're going to do this a lot in class as well, but I wanted to give you some additional notes. Number one, if anyone's absent. Number two, just if it's not making sense to you. So the unit circle is basically a circle that's located at the origin. The center is located at the origin, and its radius is 1. So that means that its points can be found at 1, 0, that would be a coordinate, then 0, 1, and then over here on the negative side we have -1, 0, and down here we have 0, -1. Now if you remember from geometry the definition or the equation of a circle, the equation of our unit circle, x squared plus y squared, because the center is at the origin, and then equals 1 because the radius is 1. And we're going to talk about that in much more detail. The words periodic and period, those we will get to, I suppose. Let me see. I don't see a definition for those right off. I mean, periodic means that it's a cyclical pattern. It repeats over and over and over again, and then the period tells you how often it repeats, but I'm sure there's a better, more mathy definition somewhere. So we're going to picture taking the real number line and wrapping it around the unit circle. So each real number corresponds, like as I go around this circle, I'm going to start at 0, and then once I get to 1, that's going to correspond to a number of radians in my circle. And as you know, a full revolution around the circle is 2 pi radians. So let me fix my camera. There we go. So the real number 2 pi corresponds to the point 1, 0 on the unit circle. So each real number t also corresponds to a what in standard position? Whose? Let's see. Oh, a central angle theta. With this interpretation of t, the arc length formula S equals r theta indicates that the arc length, since the radius is 1, is the same as the angle measure. We're going to be dealing with the 6 trig functions. So let's see. Here they're just asking us to list the abbreviation for each trig function. So we're going to, every time we see SIN, we're going to call it sine, because that's what it's short for. When we see cos, we're going to still pronounce it as cosine. So sine, cosine, and tangent are abbreviated as such. Cosecant is CSC, secant is SEC, and cotangent is COT. And cosecant is listed next to sine because it's equivalent to 1 over sine, which I'm sure they'll go over that later. Secant is 1 over cosine, and cotangent is 1 over tangent. So let's let t be a real number and let x, y be the point on the unit circle corresponding to t. So I need to sketch a picture of that for you. So here's my unit circle, and T is a point and its coordinates are x, y. So here's point T and its coordinates are x, y. So that means you're going this far, x units on the x-axis, and you're going y units up on the y-axis. And since we're in a unit circle, the radius is always 1. So you see how I can construct a right triangle out of any point on the unit circle. That's why when we start studying trigonometry back in geometry, we study right triangle trig. So here's our angle theta, and we want to complete the following definitions for our trig functions. So before I do that, anytime I'm doing right triangle trig, I always just write out my SOHCAHTOA so that I can remember my trig function definitions. But really, we talked about the movie screen, the hanging movie screen analogy, and that the sine is really the height or how big our screen is, and our cosine is really our distance away from our big comfy couch. So we could think of the sine of t as the opposite over the hypotenuse. The opposite, so if t is the point, t is also our angle, so I shouldn't have called it theta. Well, that's why they named it t. But t is really theta. It's opposite over hypotenuse, so that's going to be y over 1, or just y. So I told you the sine would be this height of our screen, and that's why it works out that way, because we're on a unit circle. And then our cosine is just going to be the adjacent over 1. So adjacent over hypotenuse, which is x over 1, which is just x. And the cosine is the distance from our couch out to the screen. Then our tangent is opposite over adjacent. So opposite is y, adjacent is x. The cotangent, now we're just looking at reciprocal properties. Cotangent is x over y. Secant, I remember secant starts with s and it goes with c. The same letters don't go together. So that's going to be 1 over x, because that's the reciprocal, and cosecant will be 1 over y. The cosecant function is the reciprocal of the sine. The cotangent is the reciprocal of the tangent. The secant is the reciprocal of the cosine. So let's complete the following table showing the correspondent between the real number t and the point xy on the unit circle when the unit circle is divided into 8 equal arcs. So we are looking at the unit circle. Let me get my camera so it's going to show everything. So here's the unit circle, and we're going to divide it into 8 pieces. So that's where we have 4 pieces already just with the quadrants, and then I'm going to make another x. So here we have 0, pi over 4, pi over 2, 3 pi over 2, pi, 5 pi over 4, sorry, is that 3 pi? That should be 3 pi over 4. 5 pi over 4, 6 pi over 4 reduces to 3 pi over 2, and then 7 pi over 4. So these are all of my 45-degree angles, and what we want to think about is that if I make a right triangle here, and this is a 45-degree angle, we have that 45, 45, 90 special right triangle thing going on. So if this is 1 unit, then both of my sides are going to be the same. It's going to be an isosceles triangle. And let me come out to the side and do the math. The side length of any side of a 45, 45, 90 triangle is just that hypotenuse divided by radical 2. We can't have a radical in the denominator. So radical 2 over radical 2 equals 1 times radical 2 is radical 2. Radical 2 times radical 2 is 2. So we get a radical 2 over 2 down here and a radical 2 over 2 over here. And so that's going to be both my x and my y. here in the first quadrant at pi over 4. And then if I go ahead and look at my x at 0, I'm 1 away from the comfy couch. I'm all the way over to the edge of the circle. And how big is my screen over there? It is non-existent. I have a nice far viewing area, but I have no screen height. So my y value is 0, which you're going to find corresponds to the sine. And my x value is 1, which corresponds to the cosine. So now if I'm looking at pi over 2, this is where my screen is right on top of my couch. I have the biggest screen I could possibly have, so that's my height, but it's 0 meters away from me, so I really can't see it very well either. And so now I'm coming over into the second quadrant. And so what we know about the second quadrant is that all of the points have a negative x value and a positive y value. So my x value for 3 pi over 4, it's going to be the same, but because it's in the second quadrant, it's negative, but my y is still positive. Then when I get over here to pi, once again I have a 0 height screen, but it's the furthest possible distance away from me. And at 5 pi over 4, now we're down in quadrant 3. And what do we know about the signs of the points in quadrant 3? All my x's are negative and my y's are negative. So therefore I'm going to have negative radical 2 over 2, negative radical 2 over 2. And then down here at 3 pi over 2, I'm at 0 on the x and negative 1 on the y. And then last but not least, here I'm in the fourth quadrant, and I know that all my x's are positive over there and all my y's are negative. So I'm going to give myself a positive x and a negative y. And when we talk about periodic functions, functions that repeat themselves, that's what we're talking about. As we go around the unit circle, the values don't change, but the signs change based on which quadrant we're in. So now I want to complete this table showing more angles than just the 45s, or the pi over 4s. Now I'm interested in the pi over 6s, pi over 3s. Basically what I'm doing is, in this chart, I'm giving all of the angles for my 30, 60, 90 triangles. So I want to, first of all, I'm going to visualize at the origin on my unit circle if I've got a 30, 60, 90 triangle. So that puts a 30 right here, and this is a 1. And so the rules of 30, 60, 90s are opposite the small angle, that's my short leg, and that's half as long as the hypotenuse. My long leg is radical 3 times whatever the short leg is. So in a when the 30 is laying is theta, these are my values for x and y. When my theta is 60 degrees, and I'm going to come, oh, and you can't see any of that, darn. Okay, and so when my theta, so there's the 30 laying flat, and there's the short leg, and there's the long leg. So those are your x's. When I've got my 60 degrees is my reference angle theta, and that just means by 30, 60, 90, and here's the unit circle, by the way. And here's the unit circle. So when I still have a radius of 1, but this time I have a pi over 3 or 60 degree angle right here. So then the short leg comes over here and it's laying down on the x-axis, and the long leg is over here on the y-axis. So just seeing these two triangles is going to help me fill in my table. So and remember, x, The distance away from our comfy couch is the cosine, and y is the sine. So at theta equals 0, I'm 1 away, but my screen height is 0. Now at pi over 6, which is equivalent to this 30-degree angle here, my x is radical 3 over 2, and my y is 1/2. But then when I get to pi over 3, that's going to switch. My x is 1/2, and then I have radical 3 over 2. And then when I get to pi over 2, I can go back and look. Pi over 2 is that 90-degree angle where we're 0 away on the x, and we're 1 away on the y. Then 2 pi over 3 is our next angle over here. And we're going to take and do a really big unit circle. So now I'm basically just going to say, okay, that negative 2 pi over 3, that corresponds, that's the same as that reference angle of pi over 3. Now, only difference is I'm here in the second quadrant. So in the second quadrant, I have negative x's and positive y's. And then 5 pi over 6 is going to be the same as that reference angle for pi over 6, except I'm going to have to deal with a negative in my x and a positive in my y. Then I get to pi, and I've got a negative 1 and a 0. 7 pi over 6 is going to go down in that third quadrant, so everything's going to be negative, and it's corresponding to that pi over the positive pi over 6. So I'm going to go negative radical 3 over 2, negative 1/2. 4 pi over 3, that's this one, and it's going to correspond to the 60-degree angle, because if I drop my triangle, that makes a 60 right there, or a pi over 3. The only thing is everything's negative. And I could also look at these two and see that they're switched with each other. Then we come down to 3 pi over 2, and that's going to be an x value of 0 and a y value of negative 1. Pi over 3, if I drop my triangle, that's going to correspond with my 60-degree angle, or my pi over 3. The only thing is it's going to be in the fourth quadrant, so the x is positive, but the y is negative. And last but not least, we have 11 pi over 6. That's going to correspond to my positive pi over 6. So I'm going to fill in those same values, but I know in the fourth quadrant my y has to be negative. So I've filled in this table right here, and now I want to be able to find these values of the different angles. So the cosine of pi over 3, I'm going to find pi over 3, and the cosine are the x values, so that's a 1/2. The tangent of 3 pi over 4, so I go up to 3 pi over 4, and I know that tangent is sine over cosine. So I'm going to have negative radical 2 over 2 divided by radical 2 over 2. That's anything divided by itself equals 1, but then one of them was negative, so that's a negative 1. And then the cosecant of 7 pi over 6, that's where I have to remind myself that that's 1 over sine. And then 7 pi over 6, so my sine is negative 1/2. So I'm just going to give a reciprocal of that, and I get negative 2. So now we want to talk about briefly the domain and period of sine and cosine. The sine function's domain is all reals, so you can plug anything in for the sine and it will give you an answer, but its range, since the radius of that circle is 1, the highest it can go is 1 and the lowest it can go is negative 1. And the cosine's domain is the same and its range is the same. The period of the sine function is 2 pi, and what that means is how long does it take to repeat itself. And the period of the cosine is also 2 pi. So that's basically saying as we go around the circle, it'll repeat itself perfectly after 2 pi. I mean, it starts to show patterns after pi over 2 or 90 degrees, but they're not exactly repeated. So which trig functions are even, which trig functions are odd? So remember about even and odd that we want to be symmetric about the origin or symmetric about one of the axes. So we want to think about the periodicity of the different functions, and we can always use the technique, which is to plug in the opposite and see if we get the same thing. So this is true, the cosine of negative t is the same as the cosine of t, and then because cosine and secant are closely related, those are even functions. So cosine and secant. And then which ones are odd? Pretty much everything else. Sine, tangent, cosecant, and cotangent. They're all odd functions. They have symmetry about the origin, but they do not have symmetry about the axis. So now we want to use the period to evaluate a sine function. So here I've got 31 pi over 6. And 31 pi over 6, I want to change that. I really don't like mixed numbers, but I want to change that to a mixed number real quick. So 6 goes into 31 5 times with 1 left over. Okay, so that's 5 1/6 pi. So we know that 1 full rotation is 2 pi. So every time we have a 2 pi, we have a repeat. So if I could take this number and the sine of 2 pi is 0. So I want to take that number and I want to think of it as the sine of 2 pi plus the sine of 2 pi plus, and now we've got 7/6 pi left over. So what I've just done is subtract out whole circles and get to where I can see the reference angle. So the sine of 7/6 pi, and let me visualize where 7/6 is, that is 1 1/6, so it's 1 full pi, which is 180, and then it's 1/6 of the way down here. So the reference angle is pi over 6, and I'm looking for the sine, so I'm looking for this height right here. So the reference angle pi over 6 is 1/2. So the fact that I'm down in the third quadrant, that tells me the sine of 7/6 is -1/2. To evaluate the secant function with a calculator, you're going to do 1 over sine. No, 1 over cosine. So you guys can do these on your own with your TI calculators. So that is all I have for you from section 4.2. That's sort of a different way of talking about the unit circle than what I'm going to do in class. So sometimes it's good to have just 2 different ways of thinking about things. Thanks for watching.